into chapter 22, quiz 1. And having said all that, the goal, my hope, I'm crossing my fingers that you will maybe take a different approach to what we're going to do starting now. What we're going to do starting now is we're going to look at 2 charged particles. And again, this is going to make a lot of sense to you because you've already watched the lecture videos. I have a charged particle on the left. I have a charged particle on the right. And then I refer to, and then again, this is from the lecture video. Then I basically have somebody standing at point P. And I refer to this point P as being occupied by sort of an anthrocentric probe called probert. So I use this term probert. Probert is basically the name. This is a fictitious name of a hired. This probert is a hired field engineer. So again, this is just my little foray into make believe. I think of probert as a hired field engineer, and probert, who is this hired field engineer, has a charge. Probert's charge Q naught is Probert's charge. This is the charge of Probert and Probert's charge. And Probert's charge is plus E, which is the fundamental charge unit. This is E is 1.602 times 10 to the minus 19th coulombs. That's what Probert is. So again, just a fictionalized character made to seem almost human-like just by my, again, flights of fancy. Probert is standing at point P, and the question is, what's the net? What is the net electric field that Probert feels at this point P? So that's the question. So from the lecture video, well, even from a long time ago, you know that the Coulomb force is K Q1 Q2 over R12 squared. This needs to be digested fully. And then here's what's new in chapter 22. The electric field, E stands for electric field, is defined as the electrostatic force divided by Q naught. This is the definition. And I'm going to kind of fast track through this because I very laboriously and meticulously talked about what the electric field is beyond just the definition in the lecture notes, lecture video, and via the lecture notes, which are kind of one and the same. All right. So this is what we're dealing with. We're dealing with the electric field. So our transition, here's our transition. We're going to go from electrostatic force, and then we're going to graduate to the electric field, and then we're going to graduate past that to electrostatic potential energy. And then our final step in sort of this unit in terms of our progression is voltage, V for voltage. And then after that, then we get into a lot of practical stuff. Then we get into capacitors, and we get into circuits and so forth. But this is the foundation of electricity, all of this right here, the electrostatic force, the electric field, electrostatic potential energy, and voltage. This is the foundation part of this course in terms of electricity. And then we have a similar sequence for magnetism, hence the term electromagnetism or electromagnetics. All right. So we are talking about the electrostatic field right now, pretty similar to gravity. Gravity, we had the gravitational force, and then we graduated. You never really talked that much about gravitational field. And then we talked about gravitational potential energy. So there is a lot of symmetry between electrostatics and gravity. All right, so Probert is standing right here. Our friend, field engineer Probert, who has a charge of plus E, is standing at point P. What is the electric field experienced by Probert at that point? So I know if I look at this left side charge, by convention, electric field lines flow into a negative charge. So I'm going to draw a whole bunch of electric field lines in 2 dimensions. If I could draw in 3 dimensions, I would. And again, the lecture video did have this drawn in 3 dimensions. All right. So by convention, electric field lines flow into a negative charge. So I'm just going to spend a lot of time drawing a whole bunch of electric field lines flowing in to that negative charge because that is the convention. So I'm just drawing a whole bunch of them. By that same convention, electric field lines flow out of a positive charge. So there's an electric field line. Here's another one. So I'm just going to play the same game and just make sure that I'm keeping in mind that if there's a positive source charge, electric field lines flow outward. If there's a negative source charge, the electric field lines flow inward. That's the convention. That's why I'm drawing things the way they are. However, from Probert's point of view, Probert does not care about any of these electric field lines except for the ones that happen to be encountering Probert. So if of all these electric field lines right here, I don't care about any of them. Probert is not affected by any of these except for this one, and I'll draw it like this, except for this electric field line that happens to be flowing in right there. This is the one and only electric field line that Probert is exposed to due to this left side source charge. Similarly, Probert doesn't care about this electric field line or this one or any of these except for the one electric field line that's emanating from this positive source charge that is encountering Probert, and it would look like that. And then if I wanted to dotted line this, it would, if I grade this out, it would be, well, okay, Probert cares about none of those except for this one. And I'm drawing the field lines sort of initiating at Probert. Because again, here's the question. What does Probert feel? What does Probert feel? Which is my way of saying, what's the electric field intent? What's the electric field strength at point P? All right, so having said all that, I'm going to get rid of all of this because things are already too messy. Okay. And we're going to start with a clean slate. And I actually have this here because maybe this is easier to view. Okay. All right. So, I guess having said that, having set the table, this is what Probert, this is what's going on at point P. All right. And I'm, again, just starting with a clear slate. So here are the 2 electric fields. In fact, what I'll do, I'm just going to index these. I'm going to call this Q1 for no apparent reason. I'm going to call this Q2. So Q1 is a negative source charge. So here's the electric field exerted here's the electric field that exists at point P due to Q1. That's saying it correctly. Ready, set, go. Actually, you know what I'm going to do? Just because I want to be hyper about this for a minute. I want to be hyper meticulous. All right, so this is my electric field line that exists at point P due to that left side source charge. That's the term source charge. So it looks like this. Okay, let's do the same thing for the right side. Again, let me just draw a little guideline here. Q2 is a positive charge. So by definition, field lines emanate outward from a positive charge. So that's going to look like this. Let me change thickness. Sorry. There. Okay, so there, eyeballing it a little bit. Let's label this. This is E1. This is the electric field at point at point P due to source charge 1. This gets labeled electric field 2. This is the electric field that exists at point P due to source charge 2. These are vectors. So let's make sure we give them a vector symbol. These are vectors. So all vector operations apply. And we're going to do that now. So this is what Probert is sensing. Probert, again, is the name I give for the field engineer sitting at point P. And Probert is saying, hey, Chris, I'm feeling two electric fields, E1 and E2. And then my response to Probert is, okay, Probert, tell me though, I don't care about E1 or E2. I just want to know, what is the net? Well, I guess here, what are the X and Y components? What are the net X and Y components of the electric field at point P? The net. All right. So that's what I want Probert to report to me. Now, what I'm going to do, there's lots of symmetry here. So for the sake of this conversation, I'm going to ignore symmetry. So I'm going to turn this problem into a 7-minute endeavor, probably into a 20-minute endeavor, because I'm going to ignore the symmetry that exists, ignore symmetry and simplifications. Because this is a very simple simplifications. This is a very simple situation that's being thrown at you in this problem. I'm going to assume that if I gave you a problem like this on exam 2, it wouldn't be quite so remedial. So I'm going to ignore symmetry and simplifications. And you can, if you don't see those simplifications now, you will. And I understand if you don't see them now because everything's new and weird. All right. So here's what I'm going to do. I'm going to pretend there is no symmetry. There is no simulations. And I'm going to do what we did in chapter 21. I'm going to create an XY force table. All right. So this is me just overlaying a Cartesian coordinate system, because this to me is a job for it. Number one, this is a job for an XY vector table. And we spent an enormous amount of time doing something quite similar in chapter 21. That was an XY vector table for the electrostatic force. This is an XY vector table for the electric field. Very similar. In fact, it's identical. All right, so before I jump into the minutiae, well, I guess I'm already in the minutiae. Is this right? So I just want to sanity check myself. I want to think out loud. And this is where you guys need to do something different. You need to actually engage with this content and ask questions and interrupt me and say, why are you doing this? Or where did this come from? Because it turns out silence isn't helpful. Being silent, it turns out not asking questions isn't beneficial. So I want to just make sure this source charge Q1 is negative. So, okay, I'm good with this being electric field line number 1. This source charge Q is Q2. Q2 is positive. So I'm fine with this being the electric field line that Probert encounters at point P, because convention. Okay. So I'm feeling good about that. Then I'm going to do my standard engineering methodology thing. I'm going to call this theta 1. I'm going to call this theta 2. Theta 2. And remember, here's the convention. The convention is as follows. Express angles. Angles, I'll say this. This is the angle convention. Unless you override it, and you can. There might be instances where we do want to not use this convention, but the angle convention is, let's measure all angles as going counterclockwise with respect to the plus X axis. Okay. So that's why I'm calling theta 2 That's why I labeled theta 2 the way I did, and that's why I labeled theta 1 the way I did. All right, so now it's time for the table. The setup, an enormous amount of time is spent on the setup, but obviously with practice, what I'm taking 40 minutes to do, you'll do in a fraction of that time. All right, so ready. This is name. This is vector. This is exactly what we did in chapter 21. And this is the X component. And this is the Y component. Okay, so name, E1. E1 is the name of this vector. E1 looks like this. There's E1. It's pointing down, and that's a quadrant 3 vector. Because remember, just to make sure, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. E1 is a quadrant 3 vector. This is the angle that is associated with E1. Like this. This should be theta 1. And then let's just call out theta 1. What is the angle of theta 1? Maybe we're gonna have to spend some time on that. I'll come back to that. So the X component is brought to you by cosine. When you think X component, you think cosine. With a special thanks to the unit circle. So this is going to be K Q1 over R1 squared. You just follow the subscripts. Cos theta. Cos theta captures the X component. Cos theta 1. This Y component, this is the beauty of this approach. It's just so methodical, so rational. This is going to be KQ1 over the distance between probert and that source charge. The distance between probert, which is point P, and source charge Q1 is R1. And then I square that. And then sine theta is what captures the Y component. Okay, done. Here's E2. And before I go on, let me just mention, when I say capture the X component, visually it looks like this. This is what cosine is doing for us. Cosine is capturing this component right here, this X component. This red vector here, this is E1X. And that's what cosine captures. This component right here, this is E1Y. Yep, E1Y. And that's what the sine function captures. Okay. And again, this was theta 1. Good to go. E2. E2 is the next vector. E2. E2 is a quadrant 2 vector. It looks like this. There's E2. This is the angle theta 2. That's theta 2. And then this is E2's X component and E2's Y component. E2X, E2Y. And that's what sine captures the Y component, cosine captures the X component. So let's just tabulate that up. This is going to be K Q2 over R2 squared cosine theta 2 all over K Q2 over R2 squared sine theta 2. All right, that's it. So then, let me zoom out. Then we just have to add them up. That's step, I'm still on step 2. So E net, and we're just making a table out of this. The net vector, E net. I don't know what it looks like, so I'm not going to write down anything. And these are vectors, so I need to indicate vector electric field 1, vector electric field vector. So electric field vector 1, electric field vector 2, and the net electric field vector. Don't know what it looks like yet, but then I'm just going to add them up. All right, so Once I have this table established, I'm just going to add the X column. So I'm just going to say, I add up all of these X components. If I add up all of those X components, I get K Q1 cos theta 1 all over R1 squared plus K Q2 cos theta 2 all over R2 squared. That's my net. This is my net. This equals E net X. So all we have to do is process that. All right, so let's do a sidebar for angles. So let's talk about angles. What is theta 1? 3, X is minus 3. So I guess we're going to have to do some trig, but let's talk about theta 1. This angle theta 1, well, I know from here to here is 180. And so I guess the question I'm going to look at now, what is that angle right there? All right, this angle here that I'll just indicate that little a. Okay, so theta 1 is going to equal 180 degrees plus little a. And then the question is, what's little a? So let's look at the geometry. I know the source charges. I know X is minus 3. All right, so this is going to be pretty easy. This dimension right here, 2 source charges. This is 3 meters. 3 meters as given. This is also 3 meters. The figure shows 2 charged particles on an x-axis at x equals -3 and x equals +3. And this point here, Probert is at 4. Okay, so this is 4 meters. So this is a 3, 4, 5 triangle because, well, I'll come back to that later. But right now, theta 1 is going to be 180 plus a. What's a? A equals angle A is going to be, I guess I'm going to use an arctan. So maybe I'll take it the long way. A tangent of angle A, looking at this right angle triangle right here. And I would maybe just draw a little assistant here and say, okay, like that. Tangent of angle A, according to SOHCAHTOA, is side opposite over side adjacent. The side opposite is 4 meters. The side adjacent is 3 meters. So angle A is going to equal the arctangent, and definitely interrupt me if I'm doing something wrong, of 4/3. Let's get a number on that. What is 4 divided by 3 arctan? Okay, 53 and some change. I'm going to write down 53 and some change, 53.13 degrees, but I'm for sure going to keep that in my calculator because I want to add 180 degrees to it. So this is going to be 180 plus 53 and some change. My numbers, maybe not yours, is 233 and some change. And that's what I want to store in my calculator. So this is going to be 233.13 degrees, and I'm going to keep this in memory location A. Store alpha A. What theta 2 is next? Theta 2 is going to equal 90 degrees plus B. So it looks like I'm calling this angle B right here. This is angle B. Angle B, it's back to SOHCAHTOA. Angle B, I'm going to do the same thing. Tangent. Again, angle B. Well, maybe I'll do it like this. Angle B here. This angle B right here. This angle B is the same as this angle B. Those are vertical angles. All right, so this angle B right here, this is a job for SOHCAHTOA. So angle B, tangent of angle B, tangent of angle B is side opposite over side adjacent. The opposite side is 3. The adjacent side is 4. So angle B is going to be the arctangent of 3/4, which is 36 and some change. 36.86 degrees. All right, so then equals, let me move this down. I have my answer for angle B. Equals 90 plus what I just figured out, 126 and some change. 126.869 whatever degrees, and I'm going to keep that in calculator memory location B. Store alpha B. Okay. All right, that's good. Let's do distances. Let's do distance. What is R1? R1 is 5. Distances. So R1 is the distance between the source charge. Here's the source charge. And prober, the point that I'm interested in. This distance right here is Pythagorean theorem says 3 squared plus 4 squared is 9 plus 16, which equals 25. So R1, in fact, I don't need to take the square root. I'm just going to say R1 squared equals 25 meters squared. What's the distance between source charge 2 and the point that I'm interested in? Well, it's right here. That's the answer. What is that distance? Same thing. 3 squared plus 4 squared is 25. So same thing. And again, this is where you're saying, trust me, I know you're saying, do you really need to do all this stuff, Chris? Because everything's symmetrical and we can really fast track this. But again, what if I gave you a completely non-symmetrical and not so simple to simplify situation? Nothing like stupidly difficult, but what if you can't make what if there's no low-hanging fruit to deal with there? All right, so interesting. The other thing I'll note right now is, and it doesn't hurt to note this, but this is the symmetry you could look at. You could say X components all cancel, or no, I'm sorry, Y components. The Y components cancel. You can see that. So this is the symmetry that you would see probably immediately. Maybe you've already seen it. And this is what I'm referring to. Here's the Y component for E2. So I'm going to label this E2 subscript Y. This is the Y component for E1. Like that. Let me make it look a little bit more precise. And I'm going to label this E1Y. So you can see that this component right here, this E2y component, is opposite and equal to E1y because the source charges have equal magnitude. The magnitude of this source charge is Q. The magnitude of this source charge is Q. So that's the symmetry. You could say, maybe we'll do that now, I guess. You could say, you would make this comment. That's why you would make, the y components cancel out. And why are you saying that? You are saying that as seen in my carefully drawn vector diagram. This is why step 1 is so important on exams. Everything is keyed off of a vector diagram. E1y, E2y cancel, they're opposite and equal as seen in my carefully drawn vector diagram. So only the x components would, and you can see just sort of like lifting up the hood. This is why right away. Okay, yes, there is no y component. Probert does not sense any electric field in the y dimension. It's all in the negative x. And it's all in the negative x because this is E2x right here. So this would be E2x. And similarly, this is E1x is right here. E1x, they're kind of overlaid on each other, but this is E1x. And you can see they are both equal and they are both pointing in the negative direction. So anyway, that's what you could take advantage of that. If you had this situation, you could take advantage of this. But again, I'm sort of taking the heavier approach. So all we have to do is add this up. So ready? Let's add up the x components to get the right answer and to troubleshoot if we're not getting the right answer. Okay. All right. So number 3, step 3 is E net x. E net x equals, what can I pull out? I can pull out some common factors. Let me indicate those now. Q1, the value of Q1 is Q. So the magnitude of charge Q1 is Q. The magnitude of Q2, that's also a Q. R1 squared is 25 meters squared. And R2 squared is also 25 meters squared. So if I'm going to pull out those common factors, I have K is a common factor. Q is a common factor. R squared, I guess I'll just write it like this. R squared. So I'll say this. R1 squared equals R2 squared. Let's just call it R squared. That's good. That's a good note to make. So what's left when I pull out those common factors? Cosine of theta 1 plus cosine of theta 2. All right. Unless I'm making a mistake, and if I am, I'll just troubleshoot. But let's go with numbers. K, this is the Coulomb constant. 8.99 times 10 to the 9th newtons meters squared per Coulomb squared. That's K. Here's Q. Q is given. Negative Q is given. It's the same as positive Q. So these are the same charges, but 4.8 times 10 to the minus 19th. 4.8 times 10 to the minus 19th coulombs. That's right. Okay. Over R squared is 25 meters squared times cosine of angle theta 1, which is alpha A, plus cosine of angle theta 2, which is calculator memory location B. And let's see what the numbers say, and then do dimensional analysis. 8.99. That's right. Okay. Answers, calculator says, and this is, you're definitely going to get a lot of good calculator workouts with these chapters. Lots of crazy big and crazy small exponents. Negative 2.07, 1296, 1296 times 10 to the minus 10th. And then I'll do dimensional analysis as you're hammering away. And again, the calculator part is oftentimes the challenge. From a dimensional analysis point of view, dA means dimensional analysis. My numerator, so here's the question: newtons meters squared over coulombs squared times coulombs, all of that over meters squared. So you know what that means? I do, in fact, end up with a Newton per coulomb. So those are my units, which I would expect. If you look at the definition of electric field is defined as force per charge. So I would expect Newton to be in the numerator and Coulomb to be in the denominator. So I'm feeling good because I got the right units. Always a confidence builder. Newton per Coulomb. So we're done. We are done. Even though I did take advantage of some symmetry. Basically, when I said this, I did sort of chicken out, and but again, what if you had a completely, I had this charge and this charge and this charge and maybe even a fourth charge, no symmetry. All these, what if all four of these, let me just do this as I'm yammering. You're still probably hammering on your calculator, but the assumption is you watch these lecture videos again anyway. So for that, I'm just going to say, hey, what if on exam 2, you had something not ridiculous? None of this is going to be, there's no ridiculous questions on these exams. They're all very much like homework problems, which are quiz problems. But what if I had this? What if I had this charge at some weird angle, then this charge at some weird angle, and then maybe another charge, and they were all different charges and no symmetry? That would be fair game. All right, so this is the answer. This is the answer to our very first quiz. Let me highlight this. And as I go on, at this point, you guys, I need to start some tough love. You need to learn what we just did. Those of you, if you were stumped by any one of those exam 1 problems, this is why. This is why. You basically did not really learn. You did not engage in deep learning at this point. So at this point in time, as I get the next quiz ready, let me just write down deep learning. You guys need to start doing the deep learning now. You need to look at everything I did with a healthy sense of skepticism. Why did I do this? And then you need to start asking questions. Now, you don't have to ask questions now, although you're welcome to, but you have to ask questions if there's anything that doesn't make sense. So this is the mission going forward. It's not getting full credit. It's actually deep learning. And trust me, there's a lot of people. There are a lot of students in your situation who are very much committed to deep learning. I'm not saying you're not. I'm saying I just maybe need to nudge you a little bit stronger into go beyond getting the right answer. So how many more colors should I add to this? I could add a few more just to stress that. Watch this, deep learning. So I'm buying time because I know some of you are still probably clicking away on your calculator, but you're going to get the right answer. I'm going to go off to quiz 2, set it up. chapter 22. Chapter 22, quiz 2 is coming at you. Chapter 22, quiz 2. Okay, chapter 22, quiz 2 is, let me fix this. It's problem 15. And chapter 22, quiz 2 is now available. It should be homework problem number 15. It should look like, oh, why do I have 13? Why does that say 2213? Let me check something. Chapter 2, homework. Homework problem number 1 is 9. All right, so we just did 9, I think. We just did homework problem 1. Okay, so everything's okay. Our next problem is 13. This one, all right, I guess this is good. All right, so let me know if you're seeing something different. I believe this is chapter 22, quiz 2. And I have just a better drawing here that I'll work off of. All right. We have 3 particles. We have 3 particles, 4 particles. Don't we? Proton. All right. We actually have 4 charged particles. We have this electron.
Professor Chris,
Yep.
I'm seeing a different question for the quiz.
Chapter 22, quiz 2.
Yes.
Okay, let me go in and fix that then.
I'm also seeing a different question.
Chapter 22, quiz 2. Okay, let me fix this. Checking. Yes, you are. Thank you. 2215. Okay. Okay, so let me fix this. Copy. All right. Okay. All right, this should be chapter 22, quiz 2. Okay. And again, thanks for speaking up, and keep speaking up if you're not seeing this. This is chapter 22, quiz 2. Again, you guys use the chat box amongst yourselves. Otherwise, unmute and talk to me. That's how we'll proceed. All right, this is chapter 22, quiz 2. Let's get started. This is going to, maybe you can move a little bit faster since this is going to be very similar. But I'm going to try to talk, I'm going to try to dwell on some new stuff. I'm going to dwell on what's different and just reinforce what's the same. And I'm just double checking something. Okay. All right. Good to go. So there. We have another series of particles. So Probert, which is the name of our fictitious field consultant, is standing at point P. And you're going to ask Probert, hey, Probert, what electric field are you experiencing as you stand there at point P? And just to be very reinforcing, Probert has a charge of 1 fundamental charge unit, which is the same as 1.602 times 10 to the minus 19th coulombs, and positive. And it has, Probert has a name. The name we give to Probert is Q naught. Or Probert has a symbol. So the name is Probert. The symbol is Q naught. And the magnitude is 1 fundamental charge, also known as 1.602 times 10 to the minus 19th coulomb. So just saying that repetitively. All right, so let's do the electric field thing. So let's index these charges. Let's just call, well, this is Q1. This is Q2. This is just my preference. This is Q3. All right, and just to reinforce the convention, Q1 is a positive charge. So by convention, electric field lines basically squirt out of Q1 in all directions, in every dimensions, in every direction in 3-dimensional space. So you would just draw an infinite number of these electric field lines emanating from Q1. But this one, the one I'm drawing right now, this is the one I care about. This is the one Probert cares about. Probert doesn't care about any of these other emanating electric field lines. Probert cares about this one right there. That's the one Probert cares about. So in fact, because I want to have everything sort of originating at Probert's location, there you go. That's it. What is the name of this electric field line? Resulting from Q1, let's just call it E1. E1. Okay. So let's play the same game for Q2. Q2, same exact story. I have electric field lines emanating in every direction under the sun in 3-dimensional space. I don't care. Probert doesn't care about any of these except for this one that encounters Probert. That one. So I'm going to draw E2, and again, we're just going to set these up. We're going to position them such that they originate at Probert's location. This would be it's a little too thick. This would be E2, the electric field line due to source charge 2. Okay, this is E2. Let me fix that. And then we'll play the same exact game for source charge 3. This is the electric field line, the electric field vector due to source charge 2. This is the electric field vector due to source charge 1. Last but not least, source charge Q3 is also positive. All right, so I don't care about this field line, but it exists. I don't care about this field line, but it exists, so on and so forth. I don't care about any of these electric field lines, and I am drawing them such that they're emanating outward. I care about this field line right here. All right, so this is what the electric field vector looks like at Probert's location. Ready, set, go. And this is E3. So there's my setup, E3, electric field vector E3. All right, even though there's lots of symmetry again, I'm going to fight the good fight. Why am I doing it this way? Because it's more difficult. That's why. During the exam, you would take the most efficient, the most efficient approach. But here, I am being purposefully, mindfully aware of the fact of the benefit of taking the harder approach, at least during the learning process. So this is a job for an XY vector table. And to be honest, I'm not sure this is actually any more difficult, especially with a bit of practice. You're going to get really efficient at doing this. All right. So there's my coordinate system because as a science person or an engineer, as a science/engineers/computer person, I like this sort of stuff. Like might be too strong, but I definitely have a natural inclination to methodology like this. So do you. Otherwise you wouldn't be taking physics. All right. So here you go. This is theta 1. So there's not a whole lot new here, to be honest. This is theta 2. So I guess I'm going to chalk this up to practice. And this is theta 3. Let's talk about angles. Theta 1, you can see theta 1 is going to be 270 degrees plus A, angle A. And right here, this is angle A. Just sitting right here. That's angle A. What is angle A? Well, I mean, life is pretty easy. Even I will sort of draw the line. This is a square. So you have a square. You have this dimension is A. This is A. This is A. So this is A and this is A. And things are getting kind of hard to look at with all of my overlaying. Let me clear the decks a little bit. That's better. Because I think I've made my point as far as the underlying electric field lines and the resulting electric field vector. Okay. But you have the recording just in case. Well, not just in case, when you review. All right. This looks better. All right. So angle A, you can tell angle A is 45 degrees. Because let me just repeat, if this is A and this is A, then this is 90 degrees. And if that's 90 degrees, this is 45 degrees because of stuff you learned in the eighth or ninth grade, I think, which is challenging because maybe you forget it. I know I would forget it. I know I do forget it. But here's a theta 1. Theta 1 is going to be 270 plus 45 is 315. 270 plus 45 is 315. Done with theta 1. What's theta 2? Theta 2, which is staring right at you, is going to be 90 degrees plus angle B. And same conversation, angle B is also 45 degrees because things are so simple. This is angle B right here. Right there. This is angle B, which is 45 degrees. So that's going to be 135 because 90 plus 45 is 135. 135 degrees. Theta 3 equals, except look, I mislabeled something. Darn it. Theta 1, theta. This should be theta 3. So I'm going to fix this. This is theta 3, that is fixed, and that's 45 degrees. All right, so let me just double check. Theta 1 is shown that I'm comfortable that theta 1 is 315 degrees. Theta 2 is the angle going to electric field vector. E2, I'm confident that that's 135 degrees. Theta 3, okay. I think this is good. Please shout out any mistakes that you can see. As long as we're doing geometry here, what is the distance? What is the distance between probert and these source charges? Because they're all the same. You can see, and I'm referring specifically to the distance between Q1 and probert, and then the distance between Q2 and probert, and the distance between Q3 and probert. Okay, so what are those distances? It's time for old school geometry again. I'm thinking, if I look at this distances, well, if this is A over 2. This is A over 2. This is A over 2. Okay, so if this dimension is A over 2, if this dimension is A over 2, then this dimension right here is going to be A over 2 root 2, right here. So that's going to be A over 2 root 2. This is just a little bit too, well, I'll do it like this. This will be A over 2 root 2, thanks to the Pythagorean theorem. Okay. So, and they're all the same. So I will kind of take advantage of that just to put a limit to the insanity. But I'm going to say the distance between probert and source charge 1 squared is the same as the distance between probert and source charge 2 squared is the same as the distance between probert and source charge 3 squared. So let's just call it R squared. And what's R squared? It's going to be A over 2 root 2. And if I square that, R squared is going to equal A squared over 2. Okay. So there. It's a lot of geometry work, but it's out of the way now. Is that right? A squared 2. Okay. So then let's finish this then. Name, vector, X and Y. The name of this vector is E1. E1 is a quadrant 4 vector. Here's E1 quadrant 4. Cosine captures that X component. So this is going to be KQ1 over R1 squared cosine theta 1. And now this is where this method really starts to pay dividends. Yes, there's a lot of setup, but there wouldn't be that much setup if you didn't ignore symmetry, but I'm purposely ignoring some symmetry now. And even that, this still can go very quickly. K Q2 R1 squared sine theta 1, and then E2. E2 is a quadrant 2 vector. It looks like this. How do I capture that X component? It's KQ2 cos theta 2 all over R2 squared. How do I capture that Y component? Well, here's the electric field. KQ2 over R2 squared. Let me just dwell on this. This is the electric field. So this is the electric field. I don't want the electric field. I want the Y component of that electric field. So that's why I am multiplying by sine theta 2, because sine captures that Y component. And let me just backtrack, and I'm doing that every time. KQ1 over R1 squared is the electric field strength due to source charge 1. I don't want that. I want the X component, which is why I then multiply by cosine of theta 1. So just in case that isn't super clear. And then we have one more vector. Vector E3 is a quadrant 1 vector. It looks like this, sitting there in quadrant 1, K Q3 cos theta 3 all over R3 squared, and KQ3 over R3 squared is the electric field component. But as soon as I multiply it by sine, that's capturing the Y component. So let me just doctor this up. This is the X component. That's the Y component. This is the X component. This is the Y component. This is the X component. This is the Y component. Okay. And then add them all up. Add them all up. So let's do that. And let's pull out some common factors. I'm going to take all of these X component vectors like that, add them all up, which looks like this. I have KQ1 cos theta 1 all over R1 squared plus, and I am taking the meticulous way, KQ2 cos theta 2 over R2 squared plus KQ3 cos theta 3 over R3 squared. So this is, what is this? This is E net. This is E net X. E net, the net electric field in the X dimension. Let's pull out common factors. So this is where things get really simple, I think. K is a common factor. R1, so this is common factor, because R1 equals R2 equals R3, and it's just A squared over 2. What else is a common factor? Q's, what are the Q's? All right, Q1 equals Q2, so this is going to, this equals E, this equals E. Q3, for me, Q3 is 2E. So check out how easy this is going to look right now. If I pull out the common factors, K times E all over R squared times cosine theta 1 plus cosine theta 2 plus 2 cosine theta 3. Let's get a number on that, and then we're almost done with numbers. Well, I'll put my numbers in here. With numbers, 8.99 times 10 to the 9th newtons coulomb squared over meter squared. All of that, that's K. All of that is over A squared over 2. Let's see, my A value, this dimension is 3.15 micrometers. So again, A is 3.15 micrometers. So I'm just going to do 3.15 times 10 to the minus 6, because a micrometer is 10 to the minus 6. A squared, so I'm just going to do A squared. That's A squared over 2. All right. So this is my numerator. This is my denominator. That's A squared over 2 times cosine of alpha A, because that's where theta 1 is sitting, plus cosine of alpha B, because that's where theta 2 is sitting, plus 2 cosine of theta 3, or calculator memory location C. So quite the workout. Let's get this number. Okay. Check. Oh, forgot something. error alert. Attention shoppers. I'd like to report a correction. I forgot E. I forgot to insert this E value right here. So there, this is K. This is A squared divided by 2, because that's what R squared is. So let me just be hyper paranoid. This is R squared. This is K. Got it. And then what I forgot to insert E, this E right here. So I'm just going to add in times 1.6 times 10 to the minus 19th coulombs. So please note that correction. Okay, so let me do this all over. One 1.6. Okay. Mm-hmm. I'm double checking something. 315 store alpha A. 135 store alpha B. Okay. I get a number. $410 and some change. 410.018 newtons per coulomb. I'm going to stick that in memory location D. Store alpha D. And because it's almost time for a break, it is time for a break, but let's fast track. Let's fast track. And you can do this, symmetry or no symmetry. When I add up all of these Y components, so what I did for X, I'm going to do for the Y components. So I'm going to take all of these Y components right here and add them all up. Okay, maybe I'll just go over here with that. When I add up all of those Y components, so again, watch what happens. If I add up all of the Y components, let me just look at this. This is going to be the same. I'll write this down. E net Y is going to be identical to E net X, except we're going to change from cosine to sine. So everywhere you see a cosine, you replace it with a sine. So I'm going to replace this with sine theta 1, sine theta 2, sine theta 3. Everything's the same, which means this is the same, sine theta 1, sine theta 2, 2 sine theta 3. So this is what I'm going to get when I do my y calculation. E net y is just going to be same thing. Well, let's just do the same calculation. Let me do this. It's going to be the same as E net x. So I'll just steal this. Copy and then paste it. Everything's the same except, as mentioned, this will be sine, this will be sine, and this will be sine. So let's get a new number for the y component. And when I do it, okay, when I do it, I get the same result. I'm going to put this in calculator memory location E. Let me double check that just because I'm paranoid. 8.99 times 10 to the 9th times 1.6 times 10 to the minus 19th times 2 divided by 3.15 times 10 to the minus 6 squared times sine alpha A plus sine alpha B plus sine alpha C. Okay, let me double check that. Six. Oh, okay. All right. So this is this is E net X. This is E net Y. This is E net X. This is E net Y. But you're not asked to solve for the components. You're asked to solve for the magnitude. Isn't that what it said? It said, what is the magnitude of the net electric field at point P? So this is it. This is your last step. You have E net X and E net Y. So just here's E net X, some X contribution. This is E net Y, some Y contribution. E net X, and this is E net Y, E net Y. And then it's just a job for Pythagoras. Pythagorean theorem, this is what you're solving for. This is E net. So a job for Pythagorean theorem. So for me, E net is just going to equal what I have there in memory location D squared plus what I have in memory location E squared, square root of that. And then you'll be done. Okay. All right. So for me, I get squared times 2 square root 579 and some change. Newtons per coulomb. All right, so that is definitely another reinforcing example on an XY vector table, especially as it applies to electric fields. I'll do this. See you at 9:35 a.m. for more quizzes. See you at 9:35 a.m. There. All right, so now we have a dipole. And let me know if you're not seeing what I think. I'm believing this is chapter 22, quiz 3. And because I have a spotty track record, please interrupt me and let me know if this is not the case. I spent a ton of time in the lecture video talking about dipoles. It turns out dipoles turn out to be super important for lots of reasons. For reasons that pertain to electronic devices, to chemistry, to life sciences. Dipoles are the water. Say no more. The water molecule is a dipolar molecule. And again, I don't want to backtrack too much just because that is the value of these lecture videos. But the fact that the water molecule is a dipole, and we all understand the criticality of a water molecule, that's a great reason right there. So our capacitors are dipolar. And again, I'm sort of stepping into the background material a little bit too much, but just can't help myself. These are dipoles, dipolar. All right. And the list goes on and on and on. Probert, you have hired Probert to stand here at point P. Probert is standing right there. So I'm just going to remind all of us that, hey, this field engineer is standing at point P. The name of the field engineer is Probert. Probert's symbol is Q0, and Probert has a charge of +1 fundamental charge unit. Okay. And so now that we know that Probert is standing at point P, let's draw the field lines. So by now, here's the field line. Here's the electric field vector. This is the electric. I use those terms interchangeably. This is and this, for example, little sidebar. If this is an electric field line, so this is an E field line, you would ask yourself, okay, if this is the electric field line, I want to know the electric field vector at, say, this point right here, just randomly selected point. And the answer would be it's tangent. So this would be the E field vector. All right. So it's the relationship between field lines and field vectors. Very important, very fundamental. Okay, so let's go back to point P. At point P, I'm going to do some overlays here. Lots of A surprising amount of geometry. This is the distance from that source charge to Probert. This is the distance from that source charge to Probert. And I'm going to just do, this is Q1. This is Q2. That's the distance. So at Probert, where Probert is standing, Probert is experiencing this electric field vector from Q1. Ready? It's a positive charge. So there. It's a little bit too thick. I'll actually do it like this, just so I can be clever. Look at. All right, this is the electric field line at point P due to Q1. So I'm going to label that. Okay, so this is E1. This is E1, electric field vector. E1. And I would say that this is the electric field vector at point P due to source charge Q1. That's a mouthful, but that's what it is. Here's the electric field line vector due to source charge Q2. I'm doing this just to keep things collinear. All right, so there is E2. All right. That's E1 and E2. Maybe I'll do a little adjustment here. All right. Maybe do a little more adjustment here. All right. So this is vector, electric field vector E2. It is a vector. And now you know what I'm going to do, because I think I've fought the good fight enough times. Aha. Well, you know, before aha, draw field vectors, draw E field vectors. I just did that. I just drew. I should probably make this a recipe. I don't know about you. Love the recipes. Draw E field vectors. The alternative to having no recipes is just complete improvisation, which there's a time and place for that. But I like to spend more time improvising versus setting up. So draw E field vectors. Done. Let's decompose them. So this does seem to be kind of a repeatable process. So if I decompose these E field vectors, here is the Y component. Well, I'll start with the X. Here's the X component for field vector E1. All right. Here's Y. I'll go back. This is Y. This is X. Okay, let me fix that a bit. So this is E1X. That's the X component of field vector E1. This is E1Y. This is the Y component of field vector E1. I'm going to do the same thing for E2, maybe change colors for clarity. This is E2X. And this is E2Y right here, overlaid. Okay. E2. So I'm done with decomposition. So great success. I've drawn my vectors. I've decomposed them. This is all very cookie cutter in a good way. So look for symmetry. Let's look for symmetry. And and I guess interference. And look for constructive and destructive interference. So this is technically a chapter 16 concept, constructive and destructive interference. Because now I'm all about making my life easier sooner rather than later. Interference. So you can see that you can see that E1x and E2x cancel. So that's huge. This vector here, because dipole, in a dipole, these two charges always have the same magnitude. So whatever the positive atom is in the dipole molecule is going to be opposite and equal to the negative atom in a dipole molecule. And what better example than H2O? H2O is dipolar. Okay. But maybe not the best example because that's 3 atoms. So let me just back off on that for a minute. So, all right. That's why I'm saying, because Q1, the magnitude of Q1 is the same as the magnitude of Q2. Yes, this component E1x and E2x cancel. These are the same. They cancel. And then there's another aha moment. Aha. Again, I can see that E1y is the same as E2y. So let's just call it EY. There. Let's keep going. Number 6. Let's figure out then. So what I'm going to do is the net electric field, at point P, which is where Probert is standing, is just going to be 2 times E sub y. I have a contribution, again, from E1y along with a contribution E2y. This is my contribution from source charge 1 and my source charge 2. So there you go. Let's figure this out then. Number 7, E net. E net equals 2 times E sub y. Here's E sub y, 2 times K, Q1 or Q2. You know what I'm going to do here? I'm just going to say the magnitude of Q1 is in fact equal to the magnitude of Q2. So let's just call it Q. Okay. So KQ over R squared. In fact, R is not a good name. I better call it A. And then I better take some angle, I guess sine theta. I gotta grab the Y component. So let me back up and make sure I'm making sense. This is KQ over R squared. But again, instead of using R, I'm using A because the electric field is KQ over R squared. I'm multiplying by 2 because of constructive interference. Constructive interference means E1y and E2y are constructively interfering with each other, meaning they're constructively working together. Sine theta captures the Y component. All right, so let's talk about what that A dimension is. Here's dimension A right here, A. Okay, so I can see, I guess let's do geometry. Geometry and dimensions. So you can see that that distance A, the distance between the source charge and probert is going to be A squared equals R squared plus D over 2 squared. Done. Actually, you know what? Let's do numbers on this now and just store it. So R squared, this dimension R is given as 0.0122 meters, converting from centimeters to meters. So I'm going to square that plus D over 2. For me, D is 2.6 times 10 to the minus 6. That's a small number. This is literally this is molecular. This is the realm of the molecule over 2. And I'm going to square that. And then whatever that number is, I'm just going to stick it there in memory location A. Okay, so let's do that now. 0.0122 squared plus 1.3 E minus 6 squared, store alpha A, and just double check. Okay, sitting there in memory location A. What about angles? Well, angles. Let me clear the decks a little bit here. Okay. Well, I think I'm going to call this. Okay, I guess I better move some things around. I'm going to move that out of the way because I need to do some overlays. Okay, so this is good. So this is my thinking. If this is angle theta, if I call this angle theta, then this is also angle theta, vertical angles. Okay, so that's pretty good. And then here's my y component. I don't want to lose track of what am I after here. I'm after the y component. So this is my y component. So this is what I'm going to do. I'm literally just going to copy and paste one of these y component vectors. Copy, paste, and that's what I'm after right here. So this is EY. It could be, which is the same. EY is the same as E1Y is the same as E2Y. All right, so there. All right, so what's theta? This could be a job for arctangent because if I do tan theta, so I'm looking at I'm looking at this theta right here, this triangle, that theta right there. So if I say the tangent of that triangle, the tangent of that angle is side opposite, which is EY, over side adjacent. Actually, I'm referring to over here. Side opposite. Let me move this. Right there. All right. So let me do this since I wandered off the path a little bit. So tangent of this angle here is side opposite, D over 2, all over side adjacent, which is R. Okay. So let me this is what I'm referring to. Let me repeat that over here. Tan theta is once again side opposite D over 2 divided by side adjacent, which is R. So then you're going to get theta equals arctan of D over 2 divided by R. Let's put that in memory location B. Okay. D over 2. Store alpha B. Just double checking. Okay. And I guess that's it. So the geometry and dimensions are dealt with. Number 8, the net electric field is going to be a doubling of that one of those Y components. So that's where the 2 comes from. 2 times 8.99 times 10 to the 9th Newton Coulomb squared per meter squared. 2kq. Here's Q. So I got 2kq. Q is 3.38 times 10 to the minus 6. So there's coulombs. 2kq all over a squared, which is just sitting there in my calculator, times sine of theta. Okay, so let me sanity check. There's 2. There's K. There's Q. Double checking. Okay, 3.38. Sine B over A squared. All right, let's see. Okay, let's see. Alpha A. Okay. Newtons per Coulomb. I'll let you do the dimensional analysis. Dipole. So that's our first dipole problem. And the direction is direction. Or if I wanted to make a direction out of this, I would just say negative J hat. Okay. Interesting how the resultant electric field at point B is actually pointing straight down. Okay. I'll leave that there while I get the next quiz ready. Dipole.
Professor Wood, I seem to be having a problem where my value for d over 2 and any subsequent things like d over 2 squared seem to be too small for my calculator to, when I'm trying to add it to r to get the a value or the tangent, it seems to just be rounding it to nothing.
Yeah, I think I know what you're talking about. What kind of calculator are you using?
TI-84 Plus Color Edition.
So you have enough horsepower. I'm using a TI-83 Ancient Edition. You're probably it's probably like if you go into mode, you're probably somehow truncating. It's a display issue. So that's a calculator setting. I don't know off the top. And if anyone else can speak up to give Luke an assist on this, you're not overwhelming your calculator. You're somehow basically rounding it to 0 or something like that. Like if I do float, like if I go into my calculator settings, I'm using float versus I'm using float 9, I guess. So I'm not saying that's what it is. I'm saying it's got to be a calculator setting, Luke. And if someone else can chime in who might have, because again, I'm using an older.
I was just kind of hoping you would know what setting it is.
Yeah, I do on a TI-83 Plus. It would be mode. So, and I don't know if this is the same. Mode, normal, float. You have that. Mode, normal, float.
Yeah, it's on normal mode and float. Weird.
Then I don't know. Other than that, I'd have to, do some detective work. Let's see. Why is my calculator 0? The calculator doesn't have enough precision to store the number, which is so small that the closest number can represent is 0.
But I know that's not true because when I'm just calculating that value by itself,
Right.
It's fine. It's only when I'm adding or processing for it.
Right. I know. TI-80.
Yeah, it's saying it. The calculator, Dan, the calculator is saying that A equals R, even though I know that's not true. It's just seems to be rounding the D over 2 values to nothing.
Right, because D was basically so small that it didn't matter. So using R worked for me, basically, because I don't know.
Yeah, well, I hear you, Dan, but this should not be too much for your calculator to deal with. But I hear what you're saying, which is a way around. But what if it wasn't? What if it wasn't? Yeah.
Yeah, because my calculator only went to like, because it was what, -11 or something, and my calculator only went to like -6, like, so for that when I did that calculation, I guess. So,
how does your calculator only go to -6?
well, just when I did that, I think it just rounded it or something.
Yeah, I'm still saying that's got to be a calculator setting, and I don't know off the top of my head what it could be other than just float normal float. Maybe you could change from normal to scientific or to engineering, and maybe what if you change from normal to scientific and you ask for 9 digits of precision, just something like that.
Yeah.
Let me keep going.
Does this work? Oh, it's all backwards. But I got for my radius, I had 0.00243, and then for my diameter, after I squared it, I had 0.8533025 e to the negative 11. And then when I added them together, it just came up as
The same
point.
thing.
Yeah.
Right.
Okay,
So it
changing it
basically
to
ignored the
scientific
calculation.
9 is showing that there is some difference between the numbers once I've added them now, instead of just rounding to no difference. So
Weird.
let's see if that works. Thanks.
Yeah, weird though. Especially since, I mean, we're working with like crazy exponents, but they're going to get a bit crazier. So keep that on your radar in terms of things to figure out, because again, it might I mean, even scientific with 9 might not be enough. I'm not sure. Maybe it is, but very perplexing. All right, let me get the next quiz set up. Quiz 4. Chapter 22, quiz 4. Is going to be different. Let's see. It's 26, isn't it? Yep. Okay. That's quiz 3. It's now 10:08. All right. I also wanted to mention that I did figure out more good news. More good news. I did figure out how to make that traffic light report a requirement, which is something I always wanted to do, but I didn't want to make it punitive. So I'm going to make it a requirement by having you turn in your completed traffic light report on with exam 2. And then just by turning in, just the act of turning in your traffic light report will earn you up to 2 points of exam credit. And I'll get into more detail, but I'm just mentioning it now because this is the traffic light report. And this is the traffic light report for exam 2. And this is the epicenter. This is the epicenter of what you guys need to do differently. You actually need to commit to the traffic light report. There's no way, there's 0 odds of probability. Your odds are 0% of not doing well on exam 2 if you take this seriously. So, and more details later, but again, it's going to be basically free points. If you turn this in, you're going to get sort of free credit. It's going to be the honor system. So you're going to complete this however you want to complete it. And I'm assuming and hoping that you're going to complete it accurately. But even if you chose not to complete it accurately or honestly, I have no way of knowing that. Either way, it's basically 2 birds with 1 stone. You're going to complete the traffic light report. You're going to turn it in with exam 2. You're going to get exam points, which is basically money for nothing. And you're going to do much better on exam 2 because you've spent some time really following the traffic light report. So stay tuned for more details. But that, to me, this is going to make a great difference. Chapter 22, quiz 4. You should be seeing chapter 22, quiz 4. It should look like this. Please let me know if it doesn't, because it might not, but I think it does. Chapter 22, quiz 4. Now we graduate. So we graduate from the following. We now have dealt with quite a bit. We've dealt with point charge. So this is we've dealt with electric fields, due to ... point charges. A single point charge, done. Point source charge, multiple point source charges. And we've spent a lot of time just on point source charges. Now we graduate. Now we're going to graduate to a line of charge. We're going to line continuous charge. Continuous charged objects. And in terms of continuous charged objects, so if I call this A and B and C, the first one would be a line or arc. And then we're going to graduate from a line or arc to a charged surface. Okay, so we are here right now. We've done part A. We've got it. We've got a good look at part A, a good look at part B. Now we're looking at part C, number 1. This is a line of charge. So Probert is standing right here at point P. And now Probert is surrounded by 2 arcs of charge. So this is a charged arc. And just like this is a charged arc. Okay. So this is a positively charged arc, which means if I wanted to play this electric field game, I would say, well, I'm going to look at every point along this top quarter arc. So let's just do that. I'm going to look at this point. What's the electric field at point P look like due to that top point? It looks like this. It's positive, so it's straight down. Got it. Then I'm going to look at maybe over here. Here's another point on this top arc, top quarter arc. What's the electric field look like due to that? It looks like this. But I'm going to play this game a few more times. Here's another differential charge. So this is a teeny, each one of these dots just represents a chunk of this quarter arc. And that's the differential calculus approach. So this charge produces this electric field vector. Got it. And then I'm going to play this game a whole bunch, many more times. And if I do that, just keep rattling out little differential charges. And from here, from that, I get this electric field line. And then from this one, I get this electric field line. So if I play this game enough, you guys, with that top quarter arc, I'm going to get electric field vectors that pretty much look kind of like this. Just sort of fanned out like that. This one kind of got away. So all of this, what you see right here, these are the electric field lines that are produced by this top quarter arc. And there's an infinite number of them. So this could get really dense. I'm going to do the same exact thing with this negative quarter arc. So same game means, well, what's going on with this point on this bottom quarter arc? Well, it's a negative charge. So those electric field lines actually look like this. I'll draw it like this. Like that. Okay. What about if I wanted just to select this, a point on this charged arc down here? Same thing. My electric field lines would look like, my electric field line there would look like this because it's negative by convention. Electric field lines always flow into a negative charge. And then I play this game 20 more times. What about this charge? What about this charge? What about this charge? So on and so forth. So I don't know how to deal with, I know how to deal with point line charge. I know how to deal with point charges. I'm really smart about point charges. So that's why I'm fragmenting this up into point charges. So then I would have an electric field line like that and so on. And there. Okay, so I just go crazy. I'm just going crazy with there. So the bottom line is, and I kind of scaled these not quite accurately. I just wanted to, let me fix that. Just to be, because they're the same as the red field line. So I'm just going to make a little adjustment so I don't mislead anyone here. This is probably good enough. And that's it. You can see what Probert is experiencing. Probert is experiencing all of these electric field lines, and already I can see some symmetry. So let's start. Number one, draw field lines. Draw a lot. Draw a lot of field lines. I've done that. This is actually an important ingredient. Draw a bunch of field lines. Good. Done. Number two, look for symmetry. Look for symmetry and this term again, constructive and destructive interference. So this is us looking to make our life easier. And I do see something. I can see that I can see the following. I can see that all electric field X components cancel. So they destructively interfere. Components cancel at point P. That's huge. All of them cancel. So let's make sure I got that right, because I'm saying, hey, look at, for every negative electric field line, I have a counterpart on the positive side in terms of the X components. So the X component of this electric field is going to be canceled with the X component of this electric field. So make sure, this is where you guys have to understand. This is where the deep learning comes in. You have to agree with the statement. And if you don't agree, you have to speak up. And if you think I'm making a mistake, you have to speak up. But right now I'm thinking all E field X components cancel at point P. So that's a huge stake in the ground. I can also say, number three, all Y field components reinforce. Number three, all electric field Y components reinforce. They basically double. They double. So let me do this. Let me get rid of all of this overlay. And let me just go back and select just two arbitrary points. I'm just going to select this point, and I guess down here, the associated point down here would be this point. Okay, so I just want to dwell on this for a second. So let's just think of these 2 points as corresponding. These are corresponding points. I'm going to move this. I'm going to get rid of that. Okay, good enough. All right, so let's look at this top point. This top point, once again, it's positively charged. So by convention, the electric field flows out of this positive charge. So let me draw a little guideline here. Like that. Good, like this. And then I'll draw a guideline here as well. Okay. So look at this top sample. This is just some arbitrary point. I mean, I'm going to draw like 100 of them, but right now I just want to draw one point, and I'm saying the following. Here's the electric field line due to that top charge. This is the electric field line E1. So I guess I'm referring to this as Q1. Here's the electric field line due to that bottom charge, E2. Looking like change pens, E2. About like that. Okay. E2. Now what I'm saying is if I decompose E1, here's the decomposition of E1. Here's the Y component. And there's the X component. So this is E1X. This is E1Y. Similarly, for E2, here's the X component, or I should say, here's the Y component for E2, that E2 vector. There's the Y component. So this is E2Y. Here's the X component. Like that. Okay, E2X. So there. Now that I've simplified things, you can see that if I just play this game and I look at corresponding points, so Q1 corresponds to Q2, which is down here. This is Q2. All right, and you can see, now I think it's easy to see how this X component from source charge 2 is opposite and equal to this X component from source charge 1. So this is, again, they destructively interfere. They cancel. All right. But on the other hand, source charge E1 produces that Y component, and source charge Q2, I should say, Q2 produces this charge. And this is why I'm saying this is why they constructively reinforce. These add together. All right, so lots of time spent on that. Let's proceed now. Now that we understand, or now that hopefully I've explained these two statements right here. The Y components double, the X components cancel. Let's go ahead and say, once again, say to ourselves, in all honesty, I know how to deal with point charges, but I don't know how to deal with line charges, lines of charge, or arcs of charge, continuously charged objects. So I'm just going to fall back onto point charge. Well, for a single point charge, one point charge, let's refer to it as DQ. Why am I calling it DQ? Because it's infinitesimally small. Infinitesimally small. It's super teeny tiny. Infinite. And misspelled that. So it's super small. It's a differential element. So let me just take 5 minutes to figure out how to spell infinitesimally. Infinitesimally. So here's what I'm going to do. DQ is super small. How's that? Super small. It's different. It's a differential element. It's infinitesimally small. I'll spend some time after class figuring out how to spell infinitesimally, but for now, DQ is super small. It's so small, it's basically, it can be considered a point. It's point sized. And I like that because I know how to deal with point sized charges. We've been doing this all along. Here's how I deal with a point sized charge. The electric field is, yes, KQ over R squared. And you know what this is going to become? I'm going to differentialize this expression. dE equals K dQ all over R squared. I like this. I'm feeling good about what I have there in step 5 because there it is. There's my electric field, K dQ. Now, number 6, what's dQ? You have here's the trick to calculus in physics and engineering, science and engineering. I have to figure out, I have to somehow cough up an integral. I have to cough up an integral, and this integral needs to capture. So that's integral. The integral needs to capture the system's geometry and material properties. That's your path. You need to capture the system's geometry and material properties. Okay. So, and that's true from this level on up into, sky level. My whole goal is to craft an integral. This means integral that captures the system's geometry and material properties. So that's the path I'm on. And for now, let's see, it's 10:27. Let's take a brief break here because this is some heavy lifting. So see you at 10:36 a.m. A nice little break. Okay. And see you at 10:36. And we're back. Good news. I'm happy to report that after extensive research, I actually figured out how to spell the word infinitesimally. So that is one of many achievements that we can chalk up to today's session. Let's continue. Because again, we're at a little bit higher level now in terms of figuring out the electric fields due to various configurations. We have dealt with a point source charge, multiple point source charges, and now a continuous charge object. Specifically, what happens if you have a line of charge, this is a line of charge. What happens if you have a arc of charge? This is an arc. So this is what we're dealing with right now. So to continue, I basically said, I don't know how to deal. The only thing I can deal with are charge points. So I said, well, I'm just going to look at a super small, infinitesimally small, also known as a point-sized charge called dq. And then step 6, I said, well, what's dq? So now here's some new thinking, because at the end of the day, I'm really liking this statement. I need to capture the system's geometry and material properties. So here's one way I can capture that. And this is a common approach for physics and engineering. So I'm going to say let lambda equals linear charge density. So what I'm doing now, this isn't just some weird, unique approach for this problem. This is a very universal approach. So I would never just spend a lot of time teaching you well, I guess I could, but this is very extensible in terms of its applicability. It's very applicable to a bunch of stuff going forward. Linear charge density means charge per length. Charge per length. And notice charge per length. Charge per length. This is a material property, and this is geometry. So that's why I'm spending time with this lambda. This is Greek letter lambda, linear charge density, charge per length. Charge per length from a macroscopic point of view is just charge per length. That's true. From a microscopic point of view, it's going to be dq over, I guess, ds. There. So let me highlight this. This is a big deal. This is macroscopically. Macroscopically means, the view from 10,000 feet. This is big picture. Big picture, yes, charge per length. And right here, this is microscopically. Microscopically, and whenever I say microscopically, that's the same thing as saying differentially. And it's also the same thing as saying infinitesimally. Infinitesimally. There, that's better. So these are all saying the same thing. Infinitesimally small means differentially small, means micro, means super small. So what's true macroscopically has to be true microscopically. And there's actually a little caveat there. This is true if uniformly charged. If uniformly charged, meaning that wherever I take a sample, the charge density is the same everywhere, no matter where I take that sample from. If uniformly charged, then I can say this. Okay. And why do I want to say it? Because again, my whole mantra is I want to capture the system's material and geometric properties. So step number 8 comes from step number 7. That means dq equals lambda times ds. And again, I like this because this is a material property. This is a geometry, a geometric property. So this is what integral calculus was made for, doing exactly what we're doing here. All right, so that's that. I'm going to update. It's time to update. It's time to update number 5. Let's update number 5. Here's the new number 5. My differential electric field, because again, I'm living in the teeny tiny super small realm, because I'm just looking at a point charge, for example, is K. And then I'm going to replace dq. So here's K. Here's dq, lambda ds, all over the distance squared, r squared. So here, let me make it exceedingly clear. I guess what I'm really saying is right here for my little sample source charge right here, right there. All right, this is my dq. Super teeny tiny. It's so small we can consider it a point charge. What's the distance between that source charge and Probert? It's this distance right here, which is given to us as small r. Okay, so that's given to us. Let me make that clear. Look at here. This is labeled. They're actually saying the radius of this arc is little r. So I'm just going to make that easier to read. This distance, the distance between that point source charge and Probert is from here all the way to Probert, and that's little r. I think that's better. Okay. All right. So how to proceed? I guess I'm going to say number 10. Number 10. What's ds? What is ds? I'm going to indicate ds. So if I'm going to zoom in, if I zoomed into this super teeny tiny source charge dq, I'm going to blow this up. I'm going to zoom in many, many times. And basically, this source charge has a size. So it's this is my source charge. I'm just chunking it up like that. Actually, maybe even that's a little bit misleading. If I zoom in, it looks like this. It's super small, maybe red. Red would be good. Right there. Perfect. What I'm drawing now has a name. The name of this is ds. I'm sorry, it has a name. It's called dq. the name of this little differential element is dq. The size of this differential element is ds. So this has a dimension of ds. This size that I'm indicating right now is differential arc length. It's super small, so small, again, that it's point sized. That's it. Okay, that's the name of this differential element. That's the size of this differential element. So I've answered the question, hopefully clearly. That's what ds is referring to. I now have a visual on it. Okay, so I think what I'm going to do now is the old birth of a radian, BOAR. Birth of a radian. BOAR stands for birth, not birth of a nation, but birth of a radian. Birth of a radian reminds us that here's the definition of radian. Radian is defined as arc length over arc radius. So from there, you guys have seen this. You've seen this. You've seen S equals R theta many times. You know S equals R theta. And just in case you don't know, I always just say, well, maybe I don't remember that, but I do know. You go ask your instructor or Google, what is a radian? A radian is S over R. So anyway, you're getting S equals R theta, but I want to differentialize it. So I want to, at the super teeny tiny realm, the microscopic realm, the differential version of S equals R theta. Just let's take the derivative. Differential is ds equals R d theta, because R is a constant. So I'm going to make that update. Why did I do number 10? I'm capturing geometry. It's all about capturing geometry and material properties. So here's my new number 9. My new number 9 says differential electric field is K, that's not changed, lambda, that's not changed. Here's something new, R d theta. R d theta is ds, and that's my numerator. Here's my denominator over R squared. So this is something. This is what I have here. Once again, this is ds. This is ds, thanks to birth of a radian and differentializing it. So that you can see that the r's cancel, and I have k lambda over r d theta. Okay, so this is real progress. Wait, I need to ignore. What am I ignoring? I need to ignore the x components. I need to ignore the x components. I'll just write it like that, and double the y components. So how do I do that? I need to go back to my visual, and I need to decompose this into x components and y components. Okay, so here's I guess I'll just look at E1 since it's kind of easier to read. This is E1. Here's the x component. Ready, set, go. That's the x component. This is the y component. Okay. This is the x component. So this is E1x. This is E1y. I am ignoring this component because for every x component going to the right, I have an x component going to the left. I'm doubling this. Double. I'm going to double that. But how do I capture that? Number 13. Number 13. I'm going to say well, I better back up. What's a good angle? I'm going to do this. This is angle theta. Angle theta. If that's angle theta, then I can say that sine of that angle theta equals side opposite E1y all over hypotenuse, which is E1, which is why I can say E1y equals E1 times sine theta. So that's this, and that should sound very familiar to you. This is like very repetitive, although it might not sound repetitive if you're not engaging in deep learning. All right, so number 14. All right, so the y component is just going to be equal to E1y, which is right here, this whole thing. And you know what I better do? I better just indicate these are differentials. So this is differential. That's a differential. Why am I calling these differentials? Because now I'm talking about the source charge resulting from this differential source charge. So just to be maybe a little more airtight, DEY equals, and that's D equals differential E1y times sine theta. So again, sine theta is capturing this y component. All right, so I think we're ready to integrate almost. Here's the new number 9, new number 11. Number 11 now becomes this differential source, this differential electric field is going to be equal to K lambda over R d theta times now sine theta. This sine theta is capturing that y component. This is my electric field once I've done some processing on it. So now that's it. This collectively is DEY. And then again, I'm going to have to double that. If I double that, I'm doubling it because I have a contribution from my top quarter arc and my bottom quarter arc. So ready, E net. The net electric field at Probert is going to equal twice the integral of the differential contribution, or twice of the integral of K lambda sine theta over R. Okay, that's it. This was, so what I have here in green, that's my integrand. Why am I integrating? Because I can't think of anything else to do. I have processed the heck out of this. Steps 1 through 16 got me to where I am right now. I'm multiplying by 2 because this is the doubling. This is the doubling of the contribution from the top quarter arc and the bottom quarter arc. And now what are my limits of integration? So I guess if I'm just dealing with the top quarter arc, I'm going to take whatever this top quarter arc is doing, I'm just going to double it. So I'm keying on the top quarter arc, which means I guess I'm going to go from this angle here, theta, this is theta equals pi over 2, to this angle here, pi. So this is what I want to basically glue together. I want to take all of these differential point source elements, this one and this one and this one and this one. I want to take all of these teeny tiny differential contributions, glue them together, and that's my net effect. So I'm going to go from, I guess it doesn't matter the order, but I know this is going to be, well, I'll say my upper bound is pi over 2, my lower bound is pi. Or you could reverse it, but I know one thing. I know right now, I know direction. So whatever the magnet, whatever the number comes out, I know the direction I know direction. It's minus j hat. It's minus y direction. Because of all of that conversation I had about, well, all the x components cancel, all the y components double, and all the y components are pointing downward. So whatever, I'm just going to take the magnitude of what I get from step 16 and know that it's in the minus y direction. So let's finish this. 17. What is the integral of sine theta? If this is sine theta, and then if I take, this is sine theta, this is cosine theta. All right, so it's cosine theta. And if you didn't know that, you would look it up, or I would give it to you. All right, so this equals 2 times, let's bring out all the, look at everything is a constant. K is a constant. Lambda is a constant. R is a constant. So I'm going to bring out all of the constants, 2 times K times lambda over R. The integral of sine theta d theta is equal to 2K lambda all over R times cos theta from my limits pi over 2 to pi, which means, keep going, E net. This is going to equal 2K lambda all over R cosine of pi over 2 minus cosine of pi. Cosine of pi over 2 is 0. This is 0. Cosine of pi is -1. So that's my answer. Number 19, I'll go over here. So here's my answer. My answer is my net electric field at point P, which is where Probert is standing, is 2 times K, 8.99 times 10 to the 9th Newton meter squared per coulomb squared. Lambda, what's lambda? Lambda is charge per length. So let me make this just a bit easier to read. Look at these numbers. So I hope our calculators are up to this. They are. So all right, so I got to read what my source charge is. Getting rid of a lot of this stuff. Okay, charge is uniformly distributed along the rod with Q equals 5.35 picocoulombs in the top half and negative 5.35 picocoulombs in the bottom half. So in terms of my linear charge density, if I'm just reading this right here, lambda is charge per length, and they just got done saying the charge is 5.35 picocoulombs. That's 10 to the minus 12 coulombs all over L. What's L? L is the distance of that quarter arc. The distance of this quarter arc, well, a quarter arc means quarter of a circumference. So this would be 2 pi r. 2 pi r is the circumference, but I don't have a circumference. I have a quarter of a circumference. So this is quite involved, isn't it? Q over L equals 5.35 E minus 12 coulombs all over, let's see, pi r, r is given as 4.3 centimeters, 0.0437 meters, pi r over 2. Okay, this is my denominator. That's my numerator. So let's just stuff this into a calculator location. This is charge density. And again, charge density, charge per length, 5.35 E minus 12 coulombs per a quarter circumference. And the circumference is 2 pi r. And all right, so I think that's good. Pi r over 2. All right, so here goes. .35 E minus 12 times 2 divided by pi. Store alpha A. It's a super small number. Let me double check. 5.35 E to the minus 12 coulombs times 2 divided by pi divided by 0.0437. Okay, that's sitting there in memory location A. So now we have lambda. All right, so I'm back to 19. So let me zoom out. All right, 2K, there's K, 2K lambda. So I just have lambda. I just figured out lambda. Lambda is sitting there in my calculator memory location A, all over R. 2K lambda over R. R for me is 0.0437, 0.0437 meters. Okay, let's see what that does. 2 times 8.99 E9. .32 and some change. 32.067 newtons per coulomb. Okay. So time check 11:01. So keep hammering on this if you need another moment. For all I know, you guys might be done, but let me leave this here for a second. Let me see. It's 11:01. Let me do a look ahead. Deep dives until 50. We'll do one more because this won't take too long. All right. This will be quiz 5. Let me set this up. Quiz 5 is that 2250. Okay. All right. Last quiz. And shifting gears. I should say, you guys, just in case it's not really clear thus far, let me really just reinforce that a lot of these solutions are going to be available to you via the deep dives. This is what the deep dives look like. So a lot of Sunday's homework is addressed in the chapter 22 deep dive folder, and there's a lot. So you guys definitely need to avail yourselves of these deep dives. These deep dives are every bit as valuable and valid as what we do during Zoom classes. So these go into exhaustive detail, which is what you want, because when it comes time to take exam 2, you need to have this level of understanding. So, which is why you can see here on the notebook here, on my notebook, look at all those deep dives. Here's all of your homework assignments. Here's all of your homework problems. There's 13 of them. Today we solved 1, 2, 3, 4. We're going to do a 5th one. So of all of these homework problems, I think all of them are going to be handled via deep dives and Zoom sessions. So that's great news, right? And the only way that's not super helpful to you is if you're not making the effort to actually learn the solution, which to be honest, a lot of you did make that decision. A lot of you guys opted to not really do the deep learning because maybe you thought you didn't need to for exam 1, but you do, and you will for exam 2. Let's do one more. Yep.
I'm looking at Wiley Plus, and it's saying Chapter 7, Quiz 5, not Chapter 22.
Good heavens. This has not been my day for Wiley Plus. Does it look like a chapter? Well, I can figure it out. This says Chapter 7. That's what happens when I just indiscriminately. No, wait a minute. Chapter 22. Chapter 22, quiz 5. Let me just double check everything. Yeah, I see what you're saying. Yes. Okay, I will fix that. That's the curse of Control V. All right. You're right. Chapter 22, quiz 5. All right. And as of in the next few moments there. All right. If you refresh, you should see it as chapter 22, quiz 5. So thanks for the heads up. Chapter 22. Oh, one sec. Oh, there it is. All right. Chapter 22, quiz 5 is available. And it is what I think it is. Let me double check that. Problem 50. Okay. All right. So let me get rid of this junk. So this is basically stepping into another subtopic within chapter 22. Chapter 22 has a few subtopics, not that many. So I keep mentioning that because don't let yourself think that, oh my God, there's like a never-ending stream of these weird categories. There's not. There's a small number of these weird categories. So this is the last of them. All right. At some instant, the velocity components of an electron moving between two charged parallel plates is given. So first thing, I'm going to draw parallel plates. And parallel plates is like a magical term because that means capacitors. Capacitors are found in animal cells, plant cells, and all sorts of electronic equipment. So that's why capacitors are really at the heart of a lot of electronics and biological systems and chemical systems. All right, so I'm drawing two parallel plates. At some instant, the velocity components of an electron moving between two charged parallel plates. So whatever this parallel plate is, they're charged plates. Okay, two charged parallel plates. Suppose the electric field between the plates is uniform and given as follows. All right, so this is the magnitude of the electric field. And this is a keyword to uniform. So here's what a uniform electric field looks like. Nice, uniform line. That's not too good. This is what this is a uniform electric field, evenly spaced. This is an example of a non-uniform electric field. Okay, so non-uniform, uniform. Okay, and they're telling you there's a uniform electric field between these plates, and it's in the J hat direction. So let's draw all of those electric field lines. And J hat means plus Y, right there. This means J hat means in the plus Y direction. You know that from your experience with unit vectors. So I'm going to draw a whole bunch of electric field lines going, maybe I'll change colors, in the positive Y direction. So here's an electric field line. And then maybe I'll just draw a bunch of them. So I have all of these electric field lines between these parallel plates pointing upward. Okay, a whole bunch of them. Uniform means evenly spaced, pointing upward because that is the direction of negative Y. I'm sorry, positive or J hat. So that's enough. Let's see. Another one and one more just for aesthetic effect. Okay, good enough. This is the electric, these are electric field lines. These are electric field lines. And if these are electric field lines, then the electric field vector looks like this. It's basically just a blending together. It's a representative. So this is the electric field line between these places. I'm just going to draw with one red vector. There it is. So in fact, I'll just label this. This is my E. This is my electric field vector. My E field vector. The difference between a field line and a field vector. A field vector is tangent to a field line at any given point. So that's my E field vector. I'm going to now just get rid of these electric field lines because things are getting too cluttered, and hopefully I've made the point clearly. Okay. So this is the electric field between the plate, and it's just uniform. It's the same everywhere. No matter where I take this reading, it's the same everywhere. Okay, so an electron is between the two plates. So here's an electron right here, just some, I guess right here. There's my electron. That's my electron. And at this moment, it has an x velocity. So here's the x velocity. Ready, set, go. This is Vx, that's my x velocity. And it has a y velocity. So here's the y velocity. That looks like this. An x velocity and a y velocity. So this is Vy. And I'll just copy and paste this vector here because I know how to do vectors. I know how to stack them head to tail, head to tail. All right, so there. Same thing. These Vy vectors are the same. All right, that's what's going on with my electron's velocity when it's between the plates. Suppose the electric field between the plates is uniform. and has this value in the j hat direction plus y direction. In unit vector notation, what's the electron's acceleration? I don't know. All right, so let's do step number one. Step number one. Part A wants you to find out the acceleration. A of the electron. The acceleration of the electron is the dollar sign. I don't know. Let's see. I'm thinking this. I'm thinking of Newton's second law. I'm thinking Newton's second law, which says F equals ma. Because if F equals ma, that means the following: A equals F over m. So I'm kind of liking that. The only problem is, what's F? Number 3. Since the definition, since the electric field itself is defined as electrostatic force per charge, then there's my expression for F. The electrostatic force acting on this electron can be written as F equals Q times E. So obviously step 3 is a simple rearranging, isolating for F. Now, number 4, here's my new number 2. My new equation 2 says the acceleration of that electron equals QE all over m. And specifically, I'm talking about the charge of an electron, which is negative E, times the electric field, which is given all over the mass of an electron, which is, I'll just write that as mass of an electron. And with even more numbers now, I have negative 1.6 times 10 to the minus 19th coulombs. That's the fundamental charge. So Q, negative E, I've taken care of negative E. That's negative E. Here's the electric field. E is given to me as 120 newtons per coulomb in that plus y direction. So I am good to go with that. And my denominator is the mass of an electron. Here's the mass of an electron, 9.11 times 10 to the minus 31st kilograms. And in the interest of time, I will assume you will do at some point the dimensional analysis. All right. Okay. Is this Q? I guess that's it. Let's get a number. Well, this is the answer to part A if all goes well. Negative 1.6 E minus 19 times 120 divided by 9.11 E minus 31. Okay. Let's put that in memory location A. And numerically, I get negative 2.107 times 10 to the 13th meters per second squared. So interesting. My electron is accelerating downward. So you're going to have to actually show that. You would be asked to show. Here's the acceleration of the electron. The acceleration of the electron is everywhere downward. Does that make sense? It does make sense. This is the acceleration of the electron. It's a vector. And remember what the lecture video said time and time again. Electric field lines always flow from a more positive region to a less positive region. Let me say that again. By convention, electric field lines flow from a more positive to less positive region. That's worth its weight in gold in terms of utility. Okay, so if this is the more negative region up here, and if you're an electron, your charge is, you have a negative charge, you're going to be repelled. You will be repulsed by this more negative region. So yeah, an acceleration of straight down does make sense because opposites attract, likes repel. This negatively charged electron is going to be repelled by this more negative region. And how do I know that's more negative? Negative because this electric field line right here by convention flows from a more positive to a less positive region. So that's a lot of thinking there. We have the answer to part A. Part B says, what happens to the electron when its x coordinate changes by 2.2 centimeters? So let me just stay here. Let me stay here on the page. And let's just do kinematics. This goes back to your other physics class. All right, so I'm going to do kinematics. I'm going to do step 5. Part B wants the following. What is electrons' velocity when delta x, it's the change in its x coordinate equals 0.022 meters. That's my number. So this is the question. What happens when this electron moves? It's going to be acted upon. It will be acted upon by an acceleration. So there's change afoot. Okay, so number 6, I'm going to say nothing's going to happen to its x velocity. Nothing happens to its x velocity because the acceleration is purely in the y direction. Vx remains unchanged. And that's because the acceleration is purely in the negative y direction. No effect. No effect. Doesn't affect Vy. Okay, number 7. Let's do this. Remember uniform accelerated motion, x initial, x final, Vx initial, Vx final. Except I need to do y, sorry. Sorry for the typo. Let me just, Vx remains unchanged because the acceleration is in the negative j hat direction, doesn't affect Vx. Sorry for the typo. So Vx is not going to change at all. So I'm going to do y initial, y final, Vy initial, Vy final, a sub y, and t. And this is just me organizing all of my kinematics variables. So what happens after my x position changes by 2.2 centimeters? Well, I'm going to use this as my starting point, 0 meters. Time check something. Okay. My y initial x doesn't, what happens? What's the when the electron, what is the electron's velocity when its x coordinate has changed? All right. So my y final is, I don't know. My initial y velocity is 3.1 E3 meters per second. Yes. My final y position is, I don't know. And technically this is my $sign. A sub y, I do know that. A sub y is sitting there in memory location A. And T is, I don't know. All right. So let me just sanity check everything here. I'm saying at this moment, I'm going to call my electron's Y position 0. It's going to change as time goes by. The initial electron Y velocity is 3.1 E3. That looks good. It's going to change though, because it's being acted upon by a vertical acceleration. So yeah, that's my $sign because Vx does not change. I do know A sub Y, got it, -2. All right. So now here's the problem. I don't have enough variables to solve, do I? I don't. So step number 8. Step number 8. Uh-oh. Stuck. Not enough variables. Not enough variables. So what to do? This is where you get creative. One idea comes to my head. I'm thinking of, let's look at the X data table. So there's always a way out of these dead ends. And you're always going to encounter a dead end, and there's always a way out of the dead end. So I'm going to skip from step 8 to step 9. Look at X. Let's look at X data. So same thing, same sort of cookie cutter approach. X initial, X final, Vx initial, Vx final, A sub X, and T. So it's the same setup. So I'm going to be, my particle is starting at what I call 0 meters. It ends up at 0.022 meters later, because they're saying, hey, what's happening after 2.2 centimeters of what happens when my electron has moved by 2.2 centimeters in the X direction? My initial X velocity is 1.9 E5 meters per second. Here's something. My X acceleration is 0 because there's no acceleration in the X dimension. It's all in the Y. So that's 0. If that's 0, then this is also 1.9 E5 meters per second. And then I'm just going to solve for time. I'm going to go over here. Step 11, find time. If I can find time, I can then use that in my Y data table. So you would be given, you have worked with the uniform accelerated motion. You've worked with the equations of uniform accelerated motion. I refer to them myself as the big 5. There's 5 of them. You don't have to have these memorized. They will be given to you on exam 2 if a problem like this appears on exam 2. But I'm going to guess that it's one of these equations. I'm going to guess this equation. X final equals X initial plus Vx initial T plus 1/2 A sub X T squared. This should look familiar to you because this is not your first physics class. This is equal to 0. So look how easy this gets. This is equal to 0. And you can see in step 14 that, yeah, you can sort of see, velocity is distance over time. If velocity is distance over time, that means time equals distance over velocity. But being more formal about it, look at step 13. Step 13 is basically saying X final equals Vx initial times time, which means here's T. T is going to equal X final over Vx initial. So with numbers, X final is 0.022. Again, distance is, with velocity is distance divided by time. Time is distance divided by velocity. And let's put this in your calculator memory location. Vxi is 1.9 E5 meters per second. Let's put this in calculator memory location B. This is the time. This is how much time ticks off the clock. 0.022 divided by 1.9 E5. That's not much time. Store alpha B. Let me redo that. What is 0.022 divided by 1.9 E5? Just doing the double check. Okay, number 15. Let's go back to, I was stuck here in number 8. So now I don't think I'm stuck because now I have time. Time now is sitting here in calculator memory location B. So this is huge. Aha. I do have time sitting there in memory location B. So step 15, once again, the equations of uniform accelerated motion, which I refer to as the big 5, these would be provided to you if there's a problem like this on exam 2. No guarantees, but I guess, what am I going to guess? I'm going to guess this. I'm going to say, well, I'm after VY final. VY final equals VY initial plus A sub Y times T. Where did this come from? You used it a lot in your prior physics class. You might not remember it all that much. Depends on how much deep learning was accomplished. But this would be given to you. There'd be like a list of these equations that's given on the exam. So I think I have my answer. Number 16 says my final y velocity equals my initial y velocity, 3.1 E3, 3.1 times 10 to the third meters per second, plus A sub y, which is sitting there in calculator memory location A. Let me check. It better be a negative number. It's not, so I have to put that in. You know what? I forgot to store it, but I'll have to redo that. Times time. Time is sitting here in memory location B because I just did that. Alpha B. All right, so once again, the x velocity doesn't change. So Vx final doesn't change. It's still going to be that same 1.9 E5, 1.9 times 10 to the 5th meters per second. And I now have a number for VYF. For me, I got to recalculate my acceleration. Negative 1.6 E minus 19 times 120 divided by 9.11 E minus 31. Store alpha A, alpha B. So 3,100 plus alpha A times alpha B is a number in the negative y. So this is I hat. And this for me is negative 2 points. So I would say 2.4, and you can enter it like this in Wiley plus 2.37, 2.437 E6 meters per second in the J hat. Okay, that's the answer to part B. Part B, notice that your x velocity does not change at all because there's no x acceleration, but your y velocity did change because it's under the influence. That's it. Let's see. This quiz is available until 12 noon. If you guys are good to go, I'm good to go. So let me leave this up. Last call for questions or comments. I'll leave this up, but